Okay, so we're going to start looking at some examples of graphing the tangent and cotangent functions. And again, we're going to do this in a very similar way to how we graph the sinusoidal functions, at least at the beginning. So we're going to catalog some information based on what's appearing here. Remember, we don't have amplitude for tangent and cotangent, so instead of calling it amplitude, I'm going to call it stretch factor, SF. That's not San Francisco, that is stretch factor. And then we're going to do the midline as well. We're going to find the period, and we're going to find phase shift. And then if there's a reflection on the graph, we'll write that down, but this one has no reflection. Stretch factor. Stretch factor is the absolute value of A, which in this case is 3. Midline. Midline comes from D. Remember, midline looks like y equals that number, 1, not just the number. What is the period? So here's where this starts to look different from the sine and cosine functions. It's not 2 pi over the absolute value of b, it's pi over the absolute value of b. In this case, b is just 1, so instead of pi, it's just going to be pi over 1, or pi. Phase shift. How do we find phase shift? C over b, which is pi over 2 over 1, and that's the same thing as pi over 2. Okay? So now, in order to sketch this thing out, we're going to start by creating our coordinate axes. And let's see, I have a phase shift to the right. It looks like I'm going to need more going on the right of my y-axis here. Okay, midline is at y equals 1, so I'm going to put 1 right there. I'm going to go like that. All right. Now, before we get to the graph, let's take a look once again at our tangent function. So we're looking for a graph that looks kind of like this. And we've had a shift in our or a phase shift in our function, and this is where the tangent function is actually slightly different than all 5 of the other functions. It's how we handle phase shift. So if you go back to your sine and cosine functions, when we graph one period of those functions, we're graphing on the interval from 0 to 2 pi. That 0 is the left endpoint of the interval that we're graphing on. And so when we find our phase shift, we're using the phase shift to move that left endpoint, that 0, around. Tangent is the only function that we graph whose parent graph, the original tangent function, doesn't actually have, the interval that we graph over doesn't have a left endpoint of 0. It has a left endpoint of negative pi over 2. 0 represents the middle of that interval. Notice it's right here, dead center of this interval that we're graphing on. So I'm going to think of this as moving the midpoint of our interval, not the entire, not the left endpoint. Okay. So what does that mean for us? Look at your phase shift. We're going to move 0 by pi over 2 units. I'm going to put that maybe like right there. Okay. I'm actually going to need a little bit more space than I gave myself. Okay. So now, what we would have normally done in a sine or a cosine function is we would have taken our period and added that to pi over 2. But remember, if I added pi over 2 to this, that would make this the left endpoint of the interval that I'm trying to graph over. And I don't want that to be the left endpoint. I want it to be the center. I want my interval to straddle that pi over 2. So what does that mean? Well, again, my period... Actually, I didn't need this after all. I'm realizing that now. My period should have a length of pi. That's what it says right here. Our period should be pi. But the pi over 2 needs to be in the middle of that interval, not on the left or right. So how do I use that to determine the left and right endpoints of this interval? Well, pi over 2 is, if it's in the middle of this, then I have to split this interval into 2 equal parts and go to the right by that amount and to the left by that amount to get that left and right endpoint. What is half of pi? Well, half of pi would be pi over 2. Coincidentally, the same thing as this number. That's just a coincidence. Don't read into that. So I'm going to be going pi over 2 units to the right, and pi over 2 units to the left to get those left and right endpoints. What's pi over 2 minus pi over 2? That would be 0. So the y-axis is going to be one of my vertical asymptotes. What's pi over 2 plus pi over 2? That's going to take me to pi. Okay? And then just like we did for the sinusoidal functions, this is my left and right endpoint. I actually want 5 labels appearing in here, which I can get by subdividing each of these little subintervals. 0 plus pi over 2 divided by 2 would be pi over 4. Pi over 2 plus pi is 3 pi over 2. Half of that would be 3 pi over 4. Okay? All right. One thing I haven't done is use my stretch factor. I'm going to use my stretch factor in a similar way to how I used my amplitude as far as the labeling of my axes go. I'm going to, from my midline, go up 3 units, which is going to take me to 4, and down 3 units, which is going to take me to -2. Okay? Now, how do I use that stretch factor? Well, going back to the table from the beginning that we used for our tangent function, I noticed that at pi over 4 and negative pi over 4, my tangent is equal to 1 and -1. On my graph, pi over 4 would be like right here. Negative pi over 4 would be right here. And notice that corresponds to these 2 points. Pi over 4, 1, negative pi over 4, -1. If I'm multiplying my tangent function by some constant, stretching this function by that factor, it's going to multiply the distance between this point and the x-axis by whatever that stretch factor is. So instead of going, instead of having a point with a y-coordinate of 1, this is going to have a y-coordinate of or it's going to be stretched by a factor of 3. Remember, the midline influences where that point is as well. So let's try and put all this together. I know I have asymptotes on the outside of my interval. I'm going to draw that asymptote in. I know at the dead center of my interval, we should be crossing our midline. So I should have a point right here at my midline. Now, I know that my stretch factor is going to take the 2 remaining points that we have to graph and scale them by a factor of 3 from my midline. So instead of going up 1 unit, I go up 3 units from 1 to 4. And I should have a point here, and then down 3 units to -2, like that. Okay? So now I have these 3 points, and I have asymptotes. Don't put a line through those 3 points, because then you'll cross your asymptotes. We know that what we want is a curve, okay, as much as you can, and it should, mine doesn't look fantastic, but it kind of illustrates the curved nature of this thing. Okay, so that's the graph of this tangent function. I'm only looking for 1 period of this function, even though there are technically more, infinitely many, that we could have, included. Let's do a cotangent graph next. One thing I wanted to point out here, when you plot these 2 points corresponding to pi over 4 and 3 pi over 4, notice I put 1 up here and 1 down here. Knowing which one goes up and which one goes down comes from whether the curve should be increasing or decreasing. Remember, the tangent function should be increasing, so as we go from left to right, these points should be going uphill. Cotangent is a decreasing function on any one of those intervals, so we have to plot those points accordingly. Same information, stretch factor, midline, period, phase shift. Okay, in this case, the stretch factor is 1, because that's what A is equal to. Midline is y equals 0. Notice that there's no plus or minus anything out here. Period. What's the period? Well, remember, period comes from pi over b, and b in this case is 3. So pi over 3. Technically, it's the absolute value of b, but b is positive already. Phase shift, 2 pi is, let's bring this up. There's a plus here. And remember, if that's a plus, then we think of this as a -2 pi. -2 pi over 3. That's c over b. -2 pi over 3. Okay, let's try and graph this now. You're going to notice in this one I just need the left side, or I need space on the left of my y-axis. Midline is y equals 0. That's the same thing as the x-axis. Stretch factor is 1, so we go up 1 and down 1 from the midline. Make some labels there. Phase shift and period. The cotangent function, notice that it's cotangent instead of tangent. Tangent, I had set up here, is the trickiest one to deal with when it comes to phase shift and period because we start from the middle of our interval instead of the left endpoint. I also said that tangent is the only function that you have to do that for, because if you come here and you look at the graph of our cotangent function, which is what we're trying to graph right now, if you take this curve and call that one period of the cotangent function, the left endpoint of that interval is 0, just like it was for the sine and cosine functions. So this is going to feel a lot more like how we graphed sine and cosine. I can actually use my phase shift directly to find the left endpoint of my interval, negative 2 pi over 3. And then to get the length of that interval, my period should be a total length of pi over 3. So negative 2 pi over 3 plus pi over 3 is going to take me to negative pi over 3, like that. So this is where my cotangent function is going to live. Then I can subdivide this into 4 equal subintervals. So if I add them up, I get negative pi, divide that by 2, I get negative pi over 2. Okay, got to do a little work with common denominators here, but what is negative pi over 2 plus negative pi over 3? Well, that would be negative 5 pi over 6. Half of that is negative 5 pi over 12. I've made this a little bit crowded. Okay, same thing over here. If I add these together, this would be negative 2 pi over 3 plus negative pi over 2. What's that equal to? That would be negative 7 pi over 6, which half of that would be negative 7 pi over 12. Okay, just like the tangent function, on the endpoints of this interval we should have asymptotes like this. Our midline is the x-axis, and the midpoint of this interval is where my graph should intersect that midline, so I'll put a point there. And then at these 2 remaining x values, these ones are going to align with our stretch factor of 1. So I need to go up 1 and down 1 from my midline to plot those points. But which of these 2 is going to send me up and which of these 2 is going to send me down? This one, negative 7 pi over 12, will send me up to 1. Negative 5 pi over 12 should send me down to negative 1. And why is it happening that way instead of how it did over here? Well, notice these points are now going downhill, they're decreasing, and that's what the cotangent graph is supposed to do. So we're going to have decreasing here, and we get a graph that looks like that. Okay? Cool. Let's do a couple more. So we're going to graph another tangent function this time, negative 2 tangent of 2x minus pi over 3. Let's get our information down. Stretch factor, midline, period, phase shift. Notice in this case I have a negative, so we're also going to see a reflection. We'll talk about what that looks like for a tangent graph. Okay, let's get the information down. Stretch factor, absolute value of a, that would be 2. Midline, looks like it's 0 again. Y equals 0 specifically. Period, pi over the absolute value of b, that would be pi over 2. Phase shift, c over b, that's pi over 3 divided by 2, which is equal to pi over 6. So that's all the information that we need. Now I'm going to create my axes, and let's think about phase shift and period. The phase shift is pi over 6, which is just a little bit to the right, but remember that's going to sit in the middle of the interval that we graph our tangent function on. So we do have to move to the left and to the right of that value. And by an amount that's well, that will end up being larger than this. So I'm going to give myself, enough space on both sides of my y-axis this time. Okay, midline is y equals 0. That's our x-axis. Stretch factor is 2, so I go up 2 and down 2 from my x-axis. Period. All right, let's come back to the period. Phase shift is pi over 6, so move 0 pi over 6 units to the right. But then remember, the period should straddle that amount for a tangent function. So pi over 6 should represent, right there, the midpoint of that interval. If the length of this interval is given by our period, which is pi over 2, I need to take the length of that interval and cut it in half, and then go that amount to the right and that amount to the left. Half of pi over 2 is pi over 4. Like that. Okay? So that means I'm taking pi over 6 and I'm adding pi over 4 to it to get this right endpoint, and subtracting pi over 4 from pi over 6 to get this left endpoint. So moving to the right first, what is pi over 6 plus pi over 4? Common denominator is 12, and adding those together, we're going to get 5 pi over 12. Half of that will be 5 pi over 24. Okay, if I subtract pi over 6 minus pi over 4, that's going to be pi over 12 minus 3 pi over 12, which is negative 2 pi over 12, or that's the same thing as negative pi over 6. Half of that will be negative pi over 12. Okay, then I need to average those intervals. So here, the common denominator is 24. This is 4 pi over 24 plus 5 pi over 24. That's 9 pi over 24. And then half of that is going to be 9 pi. Well, actually, I can simplify 9 pi over 24. That would be 3 pi over 8. Half of that would be 3 pi over 16. Problems like this one, there's a lot of fraction arithmetic to do. I know, again, I do this all mentally and talking the answer out, but you may need to write some work down on the side. Okay, and then we're going to average these two as well. Negative pi over 12 plus pi over 6 is positive pi over 12. Half of that is pi over 24. Okay, and these don't look perfectly equally spaced because, again, it's difficult to do this by hand. You just do the best that you can. All right, that's really the hardest part, is getting all of these labels down. Now we're going to create vertical asymptotes. Okay, remember for this one, the midline is the x-axis, so we expect a point here, right at the midpoint of our interval. And then it's a tangent function. A tangent function would normally be increasing, but because we have a reflection about our midline, it's going to change from increasing to decreasing, looking a little bit more like a cotangent function. So that means at these other 2 points, I need to go up to 2 here, down to negative 2 here. So my graph is going to look kind of like that. Okay. Again, it's difficult to show the curve at this scale, but you do what you can. One more example, and then we'll start talking about secant and cosecant. This time I want to graph a cotangent function. It's y equals 5, cotangent of pi x plus pi minus 1. Start out the same way as always. So stretch factor, midline, what else do we need? I'm blanking all of a sudden. Period. There we go. Phase shift. Notice there's no reflection about the x-axis on this guy. Stretch factor would be 5. Midline. We have a midline that's not the x-axis this time. Y equals negative 1. Period. Remember, that's pi over the absolute value of b. Pi over pi, which is equal to 1. And then my phase shift, because of the plus here, c is negative 1. This is, or sorry, negative pi. So this is negative pi over pi, which equals negative 1. Okay? This is a cotangent graph. So remember, the interval has a left endpoint at 0 before we shift it. So it's a little bit easier to work with cotangent than tangent. But my phase shift has me shifting by negative 1. My period has a length of 1. I can see that I'm going to need more space to the left of my y-axis here. Okay, so let's start with the midline, -1. Okay, and then my stretch factor, I go up 5 and down 5 from -1. So -1 plus 5 takes me up to 4, -1 minus 5 takes me down to -6. Okay, the x-axis now, phase shift is -1. So remember, cotangent would normally have a left endpoint on that interval that we graph it on at 0. We move it -1 units, or 1 unit to the left, which takes me to -1. The period from the left endpoint to the right endpoint should be a distance of 1, and I can see pretty clearly that would take me back to 0 again. So this is the interval I want to graph on. Midpoint would be -1/2. These values would be -1/4, -3/4. Okay, our left and right endpoints should produce asymptotes. Because the y-axis is one of my asymptotes, I'm not going to put a dashed line through it. I just need to remember that it's an asymptote. My midline was -1, so I should have a point on my midline right there, dead center. There's no reflection in this graph, and we're talking about a cotangent function, which should be going downhill instead of uphill. So at these two values, I'm going to go up here to 4, down here to -6. There's the points. Now we just put a curve through them as best you can. Okay. So a little bit different in the techniques that we use to graph them, but there is a lot of similarities in the sine and cosine functions. So hopefully, you know, it's not like completely reinventing the wheel here. We're kind of using a lot of the same ideas. That's it for tangent and cotangent for now. I want to move on to secant and cosecant. Secant and cosecant, it turns out, is going to be a lot easier to graph, because really both of those, as we're going to see, just kind of boil down to graphing a sine or a cosine function and then doing something with that. So let's start by looking at the cosecant function. Cosecant, by definition, is the reciprocal of the sine function. And so when we're graphing the cosecant function, we're first going to be looking really closely at what sine is doing. Now, these, because one of these is the reciprocal of the other, we say that these two things have an inverse relationship to each other. Compare this to something a little bit simpler looking, x and 1 over x. If x is a very large number in absolute value, and what that means is that it's very far from 0, either a very large positive number or a very small negative number, meaning very far in the negative direction, then 1 over x will be a very small number in absolute value, meaning very close to 0. So if x is very far from 0, 1 over x will be very close to 0, because this has a large denominator in absolute value. And vice versa. If x is very small, then 1 over x will be very large. There's that inverse relationship. So graphically, we have to think about what that means. If the sine function, if sine of x is very, very close to 0, then cosecant should be very, very far from 0. And that's going to produce asymptotes, just like we saw with the tangent and cotangent function. In fact, cosecant is going to be undefined anytime that sine of x is equal to 0. So everywhere that sine is equal to 0, those are going to be where we see asymptotes. And that's going to be every multiple of pi. Similar, kind of going the other direction, sine of x has maximum and minimum values. So sine of x, it has a maximum of 1 and a minimum of -1. Let's look at that maximum for a second. What if sine of x is equal to 1? What can we say about cosecant of that same x value? Well, cosecant of x is the same thing as 1 over sine of x. And if sine of x is equal to 1, then this is equal to 1 over 1, which is just 1. So in other words, if sine of x is equal to 1 for some value x, cosecant of x will also equal 1. And so what that means is that the graph of sine and cosine will share some points in common, anywhere each of them are both equal to 1. Similarly, if sine of x is equal to -1, you can do a similar derivation here to show that cosecant of x will equal -1. So that means at sine, if you look at the graph of your sine function at the maximum and minimum values, cosecant, the graph of cosecant will share points at those maximum and minimum values. And anywhere that sine of x is equal to 0, which is where it crosses the x-axis, those are going to produce asymptotes for our cosecant function. So with all of this information, how do we graph the cosecant function knowing what we know about the sine function? It's going to look like this. Okay, now there's a lot going on here, but just to make this a little bit more clear and intuitive, our goal, again, is to graph y equals cosecant of x. And we're using its relationship to the function sine of x, y equals sine of x. If I graph my sine function, that's the blue curve right here, then what did we say that we knew about the relationship between these two? Anywhere sine of x is equal to 0, which would correspond to the x-intercepts of this sine function, those are going to be the places where cosecant of x has asymptotes. So we look for the x-intercepts of our sine function, and we put asymptotes there. Then wherever sine of x has a maximum or a minimum value, cosecant of x will share a point at each of those. So the actual cosecant graph is just the green stuff, the green curves that you're seeing. The blue curve is not part of the graph of cosecant. We're using that instead as a guide for how to come up with these asymptotes and these shared points. But once we've done that, we can use those shared points and those asymptotes to create the graph of our cosecant function. Okay, secant is done in a very similar way. So to avoid going through an entire discussion on secant, we would be doing essentially the same thing, but graphing a cosine function. Remember, secant is the reciprocal of cosine. So similar relationships hold between these two. And if I were to graph a cosine function instead of a sine function like I did for cosecant, then I could still do the same thing, put asymptotes through the x-intercepts, and then use the maximum and minimum values of my cosine function to create those shared points. That creates all of these right side up and upside down U shapes. Okay? How do we take those graphs and use them to do transformed versions of those graphs? Functions of the form y equals a secant of bx minus c plus d, or same thing but with a cosecant. Really, it's the same. It's just a simple matter of doing what we did in 8.1, which I know simple matter makes it sound easier than it probably is at this point, but we just do what we did in 8.1 and graph the related sinusoidal function. If we're trying to graph a secant function, start by graphing a cosine function with the same a, b, c, and d as we had here. Okay, that cosine function will act as a guide for how we then sketch the secant function, and similar for sine. So let's run through some examples here. Actually, time-wise, I want to end this video here. Let's do some examples in the last video.